Good day, ladies and gentlemen. Today we are going to talk about electrochemical hydrogen compression. So if you're looking for some picturesque and optically pleasing video, skip that. Next time we are talking about some hydrogen vehicles again. This is not for the eyes or for the ears, but this is for the mind. This is really fascinating me. And I read a lot of papers like this one, and I want to thank the scientific community because I think it's so amazing. That's the only place for me where the world is really one. There's only one language, everything is shared, so I can read that. And these are so amazing girls and boys and men and women writing these perfect papers, always summarizing what they have read and quoting so that you can follow on their journey. Anyway, I'm going to quote some papers from Delaware, USA, Eindhoven, Pakistan, also Korea, and one very good one from Mexico. So thank you to those ones. And now we have to go back to kind of the basics. And today I'm gonna make it old school with pen and paper. Those who have seen my video on the reversible fuel cell might remember that the fuel cell is made from anode and cathode. There's the membrane, there's maybe the flow field anyway. There's hydrogen coming in at one side. There is electricity coming out. This is the fuel cell. It is actually about 0.6 volt per cell, and what comes out is a mixture of vapor and liquid water when we put in oxygen from the surrounding. And actually there is some circulation here through the flow field. So here we have platinum catalysts on both sides. We have the Nafion membrane. We have the water accumulation here. We have maybe 2 bar on this side and 1 bar on this side, or ambient pressure. Those who watched my video about the electrolyzer unpacking, they saw that it also consists of many cells with anodes and cathodes. We have a membrane. We put in water. We have iridium as catalyst on the water side. We have platinum as catalyst on the hydrogen side. There's the oxygen coming out on the water side. It's bubbling out of the bubbler. And on the water side, we have about ambient pressure. And on the hydrogen side, we have 30 bar. And so here comes out hydrogen and water. So this is my way to draw the vapor. So here we have the liquid water kind of coming in. It's actually flooded. And we put in about everything. This is really not scientific. This is just a rule of thumb. We put in 2 volts and we get hydrogen from water, basically. We can also harvest oxygen in the VOLKS-ELECTROLYZER. Electrochemical hydrogen compression, which in short is just EHC. And there also we have anode and cathode. This time we put in about 0.4 volt. We have again the membrane, this time platinum and platinum. We give in hydrogen pure or non-pure. So this is not only electrochemical hydrogen compression, this is also purification. What happens? We get out hydrogen at high pressure. The maximum is 50 bar on this side, 1 bar or 10 bar, wherever you start. Most likely you start from the electrolyzer, so you start from 30 bar. Anyway, the thing is, I told you this is also purification. And now if you compare fuel cell, you have water, electrolyzer, you have water. Where's the water here? If I put in, for instance, methane and I want to purify it, I certainly recognize that if the hydrogen is then going outwards, there is something missing. Actually, there's missing H2O, because then what I get out is not only maybe hydrogen, it's also carbon monoxide or carbon dioxide, right? Interesting thing is they discovered that the CO poisoning is reversible. So if you put in methane, it gives out hydrogen at higher pressure, and there's, for instance, carbon monoxide, you can flush it with oxygen. You take the oxygen from electrolysis, and then it will take the carbon which poisoned the gas diffusion layer and your catalysts. Anyway, I think that is so amazing because you have no moving parts. It is actually, other than the other processes, so this gives off heat, this gives off heat, but this is technically, they call it isothermal, I think. So this is exothermal, and hydrogen compressor is also exothermal, so most likely your compression piston head will get cooled. So let's see how the smart guys describe that. So I will go through some pictures here. Here you see the same thing. You have the hydrogen at low pressure. The hydrogen molecule gets separated into hydrogen ions and protons, and then on the other side reconnects to molecular hydrogen. And here you also see something which is very important. It's back diffusion, which is bad on efficiency. So anyway, you see also here you need a flow field, and that's what this guy actually is analyzing, because there's very high pressure on this flow field, and there are different designs, but he has this meander. Here you see the stress on the membrane. So this is the flow field channel, and if there's 50 bar here and 10 bar here, then you have very much pressure difference. So this is one cell design for a single cell. So you have the end plates, maybe you have a gasket, a current collector where you put in your plus and minus. This is the flow field. You see this is the channel. So there's this gasket. Go a little bit closer to the membrane itself. Here we're talking about a zero gap membrane, they say. I wrote down we can use a lot of membranes like Nafion 212, 117. They spotted the platinum catalyst. The other one maybe just use this ink spreading technology. Here we now go very deep into the proton exchange membrane, and it's a polymer. Yeah, we see lots of carbon in a chain. That's a polymer. We can also say plastic. It's fluorinated. That is sulfuric acid. That is why your catalyst needs to be so corrosion resistant, because this is very acidic. But of course we want to see how it looks like in real life, and here you see maybe Nafion. If you watched the video about how to make the membrane, 5 tips on how to improve your hydrogen generator, then you will see that this is kind of a jelly material when it gets wet, right? So water and this, because only with the water you can have the sulfuric acid belonging together. Because of the high pressures here, they are describing external support, but additionally some meshes, very complicated meshes to support the membrane. You have this excellent picture like a non-supported membrane. This is after very, very rugged support. You can put a weight on and it's kind of rigid. I want to talk about multicell. designs, because it doesn't make a big flow if you have just one membrane and go from 1 to 50 bar. Maybe you want to have a bigger flow. So this is a question more or less to the scientific community. I calculated this 0.442 liters per hour and square centimeter of membrane surface belonging to this, let's say 1 amp. Maybe I'm mistaken. Please let me know in the comments. Anyway, so what you do is you put the cells in parallel, right? You get from 1 to 50 bar here, from 1 to 50 bar here, and 1 to 50 bar here, and there you get it out. 1 to 50 is not enough. So in a string that's in series, kind of without this, to get 1 to 50, 50 to, let's say, 100, and 100 to 300. This is completely, parallel. So this is equivalent to just a bigger membrane. So, and if we sum this up, this parallel and series, so this stands for parallel. So there, if you put it parallel, you don't get high pressures in bar, but what the scientists call flux, I would call flow. You get a very high flow at low pressures. This is for in series, and if you put the cells in series, you have a very little flow, flux, and you can reach high pressures. Now we get to the few pictures. So there are basically two companies ever built something commercially, and one in Netherlands and one in United States. And here you see how this actually looks like. When I look at these pipings, I think that's more like temperature regulation, where we come to a very big point, because this is temperature dependent. Here you see the end plates, and you see many ports in the parallel cell. So maybe, I don't know how many cells this might be, but some of these ports can be for heat, and some of these ports can be like pressure relief valves, so you cannot ruin the membrane, and some are. When you look here, some are the output ports. So here you have a very strange design where you got 900 bar, 50 square centimeters. That's twice the size of the VOLKS electrolyzer. VOLKS electrolyzer is 28 square centimeters. Enormous end plates due to nuts and bolts, they say. So here's some assumptions about scale effects. So now the water, so it's kind of a problem, because in this process, basically, we wouldn't have any water if we do not put in water, or we have very moist hydrogen. So that's why I like the idea of having the electrolyzer here, getting the moist hydrogen and water in here, having maybe a recirculation, and there will be hopefully some diffusion. So if you put the water trap, for instance, a little higher, you will even have a float. So I read different stuff. So you can float the anode, you can fill this with water, and the hydrogen will just bubble through the side, which is obviously possible, but then you have very, very, very much water in the high pressure gas. So yeah, I rather like this design, putting the float ball valve a little higher, that maybe you have it flooded until here, you get the most moist hydrogen in, the membrane is wet. Yeah, and from time to time you purge a little water, which you can then put back into your electrolysis, right? So some designs, I think these are like museum designs. Nobody would build a real machine like that, but yeah, if you enjoy it, you can do it. So I hope you found that interesting. Thank you so much for sticking with me. Maybe write bingo in the comments if you watched until here. And next time, I promise, there's going to be some vehicles or some more action. See you then.